It's very nice for me to be here in ASML because indeed my alma mater is Eindhoven University, and it's very nice to be back. I'll not spend so much time on myself. I'm a researcher and I research process mining. This is something different from the commercial applications that you often see in process mining. So if you heard about process mining and you know about Celonis and academical process mining is not the same thing. That's something I usually like to stress. I will not go into details about that academical debate. If you want to know more about my research, please visit my homepage, where I list a lot of my blah 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 publications. So let's talk about process mining. I will briefly talk about process mining. So what it is, how I look at process mining essentially, and then I will show you a bit of how to do it in Python. And I would like to start by focusing on this notion of process, which is a very important thing in process mining. And I want to take you through that notion of processes by means of what I kind of did this morning. So in order to get to the stage, I executed a few activities. The most painful activity, since I live in Aachen these days, which is in Germany and it's not very close to Eindhoven, is I had to wake up relatively early to be here in time. And then, as you see, I'm all dressed, so I had to take a shower. I wanted to be fresh and took a shower and I put on my clothes. I had some small breakfast, brushed my teeth. In the end, I also drove here and I was very unlucky because this highway, the A2, had a little block, so I was almost too late actually, and finally I'm here with the microphone in my collar. So when we look at all these things, these are kind of all, you could say, activities. Like, waking up is an activity that tends to take a long time, but I try to be good for the environment, so I shower relatively fast, etc. So all of these activities, they have a duration. But moreover, more importantly, there are sometimes explicit and sometimes implicit relations among these activities. So for example, I prefer to first have my breakfast and then brush my teeth. This is not really necessary, but I usually do it like that. And what is more necessary is that I take a shower first before putting on my clothes, because if I would do it the other way around, that would not be so convenient. Obviously, I cannot do anything of this prior to be actually awake. And finally, you don't want to, maybe you do, but I assume you don't want to see me presenting naked, so I did all these things before I was here. So that comes to the conclusion that a process in process mining is actually a collection of activities that we perform in order to achieve a certain goal. And the goal of my example was to be here today and to talk to you guys. But when we look in a more abstract sense to processes in organizations, you can think of a lot of goals that a company might have. But what's really important is that when I talk about processes and when I talk about process mining, I talk in the end about analyzing, as we will see later, data that's coming from these type of processes. And the more mathematically inclined people will probably know, and I assume all of you are, that these are discrete processes. So I'm not really talking in that sense about continuous processes. Although you can, of course, discretize continuous processes into this form. So, what types of processes can you think of outside of my morning routine? Think of logistics. Think of sending a package to a customer from our warehouse. And when we do that, during the, let's say, journey of the package, there will be several times in which this package is being scanned. Think of mortgage, for example. Think of financial institutions where if I want to buy a house, I need a mortgage. And to do so, I need to go to the bank. And the bank then has to decide whether I'm allowed to get this mortgage, yes or no. So what will happen is when I go to the bank and I will talk with someone, some employee of the bank, that employee, the system of the bank, etc., that will start to execute a process to determine whether I'm allowed to get this mortgage or not. Also, you can think about the hospital or the medical domain, where actually we treat patients, we execute activities in order to achieve the goal of, let's say, getting the patient out of the hospital, preferably alive. And you can think of more electronic oriented, you can think of customers going to a web shop, browsing pages, adding stuff to their basket, and in the end, receiving goods. So all of these processes have a common modern day, in the modern world, these processes have something in common, which they don't have in common with my example process. So when I woke up this morning and when I did my things to get here, I didn't record anything I did. These things just happened, and there's no data. But in modern day information systems, what you typically see is that a lot of the activities that we perform in the context of any of these processes are actually stored inside of the information system of the companies. And in process mining, obviously, because it's a very data-driven thing to do, we analyze these data tables that you see here on the right-hand side of the slide. And I'll briefly explain later how this data looks and how we work with that. But keep in mind, the data that we analyze in process mining is always assumed to be coming from the execution of a primarily discrete process. So the mining phase for all of you should be very, very natural. That meaning it's exactly like this. But then what we do is we do it like this. So what you see on the left-hand side is you see a guy that is trying to find valuable information out of this raw rock. And he's using a tool for that. And essentially, that's what we do in process mining as well. So the rock is kind of this raw data that you see in the information system of the company. The machine would be your laptop or your server running at Hadoop or Spark cluster or whatever, preferably with Python. But okay, you can also use Java, whatever you want. And then the guy is essentially this data scientist having a lot of fun in his job. So process mining, if you would like quantify it in one sentence, it's about obtaining knowledge of and insights in processes by means of analyzing the event data generated during the execution of the process. Now, why am I saying this? It's very important because you always have to keep in the back of your mind, in my view, when you do something with process mining related technology, that in the end what you want is to get more knowledge and more insights in a process in order to make it better. I think in general in data science that's always what you want to do. You want to generate somehow a knowledge out of some raw rock of data in order to streamline something. But in this case it's processes. And I have to mention specifically that this knowledge and insights is something what's really important in the context of process mining. So the analysis we do on the basis of data, in the end we try to communicate this with real stakeholders, with people. So it often doesn't suffice to just train a neural network and then say, here's your neural network, have fun predicting. Okay, so let's briefly look at the data. And let's assume, and I will be using a sort of running example in my presentation, and let's assume we own some store and we sell some gifts for Christmas. And what we're doing in our warehouse is we're putting these Christmas gifts into boxes and shipping them to our customers. And then when I would look into the data or into the information system of my company, in a simplified way, what I would see is something like this. I have 3 columns. One listing the unique ID of an order that someone placed to get a new toy for his kid. That's the first column. The second column is the activity, is what activity has been performed for that specific order. And the third column represents at what point in time. So if we look a bit closer to this data, we see that for an order identified by ZHT4574658, there were 3 activities performed, apparently yesterday in European time, 15 past 5, 12 to 6, and 9 to 6. And these activities are create order, add item, submit order. For those of you that have been working with more sequential-oriented data, this is somehow the same type of data that you would use in sequential pattern mining, but the difference is that you only use singletons rather than sets of arbitrary size. So if we look at this other order, you see that an order was created and an item was added. So this is the type of data that we work with. And we want to do a few things with that data, gaining knowledge and insights in the process. So what do we do? There are a few other things that we do. But today I'm specifically focusing on 2 subtasks that we do in process mining because these are both supported by the Python framework that I will also briefly talk about, whereas some more advanced techniques are not yet there. In general, we have 2 So we have two core components, which are process discovery and conformance checking. I will explain each of them with a simple example, and later I'll show how to do that in Python. So first, let's focus on process discovery. It is analogous exactly to this. Taking a picture, like a satellite picture out of the sky, and drawing a map. This is literally what process discovery is all about. And as I said before, here again you see a map like this of this geographic data is intended for us to reason about what we see in the real world. And that's very important. That's also what we really want to do in process discovery. So this map on the right-hand side really helps me to understand the picture I see on the left. At the same time, there are some limitations that are also inherently there when you apply this on real data. That is that if you look at this picture, it's just a, let's say, a snapshot. It's not the total surroundings of Eindhoven. So in my picture, I will also not see the total surroundings of Eindhoven. And this is the same when you apply this process discovery in real data. If you extract data from an information system, it does not necessarily show the full process. I was recently involved in a study where we were analyzing repairs of large-scale energy production facilities, and there the repair itself was not logged in the information system. And that often happens, that certain parts of a process are not visible. And the same, on this picture I can see the outsides of the buildings. I cannot see what is inside a building. And this is the same in real data. If I see that a resource is working, can be a human or a machine, I do not necessarily know if it's working slow, what is the underlying cause. It could be that this person is depressed, or it could be that this person is also involved in a lot of other processes. So that's why I like this analogy. So if I apply that on the data I showed you, and if I would generate a bit more data, then actually what we get is a picture that looks like this. It's important to realize these algorithms do that completely automatically, but since I'm talking at a PyData conference, I guess you guys understand that very well. So we push in a table with 100,000 millions of these rows, and we get a model like this. So what does this model tell us? In this case, I don't know if anyone here is familiar with the notion of Petri nets. This is sort of a form of a Petri net. Essentially, this says that on the basis of the data that I've given to the algorithm, any of these orders in our warehouse starts with a create order activity. After that, you should see an item being added to the order, and potentially such item can be removed, and you can also add multiple items. And then at some point you decide to submit the order. And now what's interesting and what's also very difficult in process mining and process discovery is that if we go a bit further, and I'll walk to the other side here, this is a block of concurrent or parallel behavior. And what you see here is that sending the invoice and potentially sending some reminders is something that we do as a company. It's our warehouse doing that. At the same time, but it's related to customer contact. At the same time, if you look at the bottom, you see that we also need to check the stock, potentially order the goods, and finally pack the order. And this is something that can happen completely independent of each other. So I can do sending the invoice at the same time as check stock, before or after it. And the same for sending reminders. It's completely independent of each other. And then finally, you either cancel, dispatch the order, and close the order. And why I'm highlighting this is that you have to realize that if you are able to schedule activities in a concurrent construct like this, the number of ways in which you can permutate these different activities, in which you can schedule them, grows factorially. So if you have 10 activities in parallel, and you could easily draw that on the slide here, it generates millions and millions of different sequences you can generate. So this process discovery, to relate it back to more classical data mining, is actually very, very difficult. And I'll try to illustrate why. So this example that I show you here is based on very clean synthetic data, and I get this beautiful picture. But if I do this in the real world, I'm just going to this information system and I'm extracting the data. The problem is that the models we want to mine are models that just describe how the process is supposed to be executed, and in such a way that it's supported by the statistics we see in the data. However, often we see in the data several data quality problems. You see that stuff is logged incorrectly. Sometimes the logging is correct, but the execution is not okay. Then the third thing that can happen is sometimes stuff is very infrequently executed but still correct. So what I said before, if you have parallel activities and you have millions of ways to schedule this, it's not necessarily the case that even though this is possible, that you will see everything. So in a way, if you just extract data and apply these techniques, what you're essentially doing is trying to learn either a decision tree or a neural network or whatever to classify whether people smoke or not without providing the actual label of whether someone smokes or not. So it's not even a single class prediction type of thing you're doing. If you do it on raw data, it's an unknown class prediction type. So it's extremely difficult, and recent research also shows one of the PhDs I co-supervised that if you want to pre-process this data in a completely autonomous, automated way, this is almost impossible to do because you cannot really distinguish easily between infrequent correct behavior and infrequent incorrect behavior, etc. So of course this picture is nice, but I think also if you look in commercial applications of process mining, you will often see that they don't support finding concurrency in this way, and this is just because it's just not so simple. As a scientist, it's great because it's fun to try to solve difficult problems. Then let's take a look at conformance checking. Conformance checking is essentially what you see on this picture. Usually I have to explain this picture because I'm also talking a lot abroad. In the Netherlands, this picture is, if you were talking in the Netherlands, for most people this picture is clear. What you see here is, of course, a pedestrian area, and the government kind of has a reference model that tells us this is what you're supposed to do or what you're not supposed to do. And obviously what we're not supposed to do is to cycle here. Yet reality, which is the equivalent here of the data, shows us otherwise. And this is something that is still a core kind of thing that we can do in process mining, but it's again alleviating on data and trying to show value, but it's much further off classical data mining in a sense. So computing statistics like this, so let's take a look again. Assume we have this order where we see that first the order was created, then the item was removed, and then the item was added. That's weird because as I hope you remember that, and I will show you a few slides back, what we try to do is always first create an order, then add an item, and then optionally we can remove an item or add more items. So what we see here is creating the order, then removing an item is not possible according to data. Then we see an add item activity and then a send invoice. And these conformance checking techniques, they allow us to compute whether or not these executions are actually in line with that process model or not. So for example, if I would feed this type of algorithms this sequence of data for this order ID, it would essentially tell me that this add item activity here should be in between, because I cannot remove items that were never added. And at the same time, it would also recognize that to be able to do the send invoice, I should first have a submit order. Now, this is, as I said, it's not such a classical data mining technique. At the same time, to compute these statistics, we actually use a lot of artificial intelligence type of algorithms. So for the more people that are a bit into that field, if you want to compute a explanation of such a trace in terms of such a model, what you're actually doing is you're solving the shortest path problem on the state space of that model in conjunction actually with a model of that trace. So you make a more refined model of the combination of the two, you compute the state space, and you do, for example, A star on this. Now the problem is that I just told you, if you have a model which is having a lot of parallelism, the state space is huge. Typically, we try to use models that do not have an infinite state space. Although there are ways to cope with infinite state spaces. There, okay. So essentially, as I said, you can see where deviations are by computing these type of statistics. What's also, of course, we use this somehow if you have a event data set and you learn a model using process discovery, we also use these artifacts to compute how well does this model describe the behavior we see in the event log. So if everything would be green, you have in a way a recall of 1. We usually call this replay fitness, but it's actually a sort of equivalent metric to recall. Okay, so process mining and this consisting of discovery and conformance checking. As I said, there are some alternative techniques as well. So there's all kinds of techniques that allow you to, for example, plot the execution of historical data onto a model to visualize that. There's also all kinds of techniques that kind of figure out if there's choices in a process, which data attributes relate to such a choice, but that's more like solving a classical data mining problem. I want to now focus shortly on doing this in Python, because in the end this is a Pythonic conference. So we started, like roughly 1 year ago, we started this PM4PY library, process mining for Python. The website that you would reach now, if you go here, is the old website, which is very funny to look at because it's this typical academical, very ugly website. It does not have the first logo, but this logo we have here is still extremely ugly. We try to make it a bit more professional, but our main task is actually writing papers, so we have little time to do that. So this is a library that essentially tries to implement process discovery algorithms and process mining algorithms, in Python. The actual intent initially was really to support academics, actually, because we noticed that there were a lot of algorithms that we would like to use in our research that were only available in Python, and there was no proper library to do this type of things. We're now also building some web-based, so with Flask and Angular, we're building some web-based client on top of this, but that is not open source, so only the basic library is open source. So let's look at some things we can do in this data, in this library. First of all, loading data. We support also Parquet files, I believe, but I just listed CSV, which is very known to most people. So if I take a look at this example data set in CSV, this would be kind of looking something like this, where the first column is again this order ID, it's called case, then we see events, timestamp, we have actually start, complete time, we have also resource information. Doesn't really matter, so if you have a data set, what's mostly important is if you have a data set that at least has such a case column or such order ID column, you have events and you have your at least start and or end time, you can kind of use this library. So try to remember what you need to do process mining, and then rather than being too technology driven, try to solve a problem with the technology that really fits the problem. So if you have this type of data, you might be able to do something with this technology. Then if you would like to load that into PM4PY, you can just essentially import the factory of the pm4py.objects.log.importer.csv class. Actually, I used the name factory initially when I started this library, and I was building something and I was using a factory design pattern for that, and then somehow some people joined the consortium and started to greatly adopting this factory idea, but these factories that we have now in our framework are actually not so much of a factory software design pattern anymore, so we might in the future change the name of this factory to something like entry point or algorithm. But anyway, so if you implement this CSV log importer, what you essentially need to do is to say CSV log importer.apply, you do the path to the file, and then if you would do that, essentially it's loaded. So this is usually is this loaded as some pandas data frame. depends a bit. Alternatively, you can use XCS. This is a, let's say, international standard for process mining data. It's an XML-based storage format, and as you can see, the difference here, although I didn't explicitly highlight that in the previous slide, is that in the previous slide you can put, so let's say in CSVs, it doesn't matter if you have an order, and it's followed by different orders, and then you have something that relates to the same order again. That doesn't matter, because there the gluing the different activities together is really done on the basis of the values. So what I'm trying to say is it could be that in between these two events here, there's a lot of different stuff, for example, for case 63, that doesn't really matter. This storage format first already groups all the different events related to the same case into one node, essentially, in the tree. So everything you see here relates to the order with name or ID 236. However, I just wanted to show actually that in CSV importing, what you need to do is type this. Then if you want to import such a file, the only thing you essentially need to change is this CSV becomes XCS, and then that's it. However, as I said, because we in a XCS file store the data on a case-by-case level rather on an event-by-event level, if you here print the 0th element of our event data, it's actually a complete sequence of it's a complete sequence of events already, rather than having the events individually. So this is all the events related to case 236. These are all the events related to case 63. Okay, so if you want to do process discovery, it gets a bit more involved. We have again our XCS file importer in this case, and we have a discovery algorithm which is called the inductive miner. There are several different discovery algorithms available. So there's also a miner called the alpha miner. So if you would swap inductive for alpha, the main usage of the framework remains the same. So essentially what you need to do is you say, I want to discover a process model. These two markings, please ignore them. It's just some side product that you get because the models we discover are patrinets, which need these side objects. However, if I run this, I simply get, of course, I just get an object back. This process model is stored in an object. So if I want to visualize the patrinet, I also need to import a patrinet visualization factory and essentially push the model into that here. So here I make a visualization by applying the visualizer factory with the model, the marking, and I say I want it SVG, and then if I call the view method, I can essentially get this model. So with these few lines of code, you can actually translate a data set into such a process model, which is nice, because for those who ever used something with process mining and those who ever used with PROM framework, which was written in Java, you would need to do a lot more. So in the case you would like to use CSV instead of XCS, what you essentially need is you need a bit more. So actually, it's not so much that is changing with respect to discovering on the basis of XCS. However, you need to specify to the algorithm which column is used to represent the case. So which column would be the order and which column is the actual event. And then if you do that, yeah.
So the data you put in here, is it already ordered on timestamp, or does it automatically detect the timestamp? Because you have to order it on.
Yeah, so what you typically, most likely it will just, I think it will just keep it the order as is in file. But it depends a bit. So a colleague of mine has also been playing around with pandas data frames. So initially what I built is that I would literally, I made an interface that essentially is just a list. So you could apply these days you have lambda functions. So my idea was, okay, if you want to sort it on any attribute that is commonly present, you just write your lambda function on this event log and it automatically works because you know it is like this. So for that interface that I wrote, it's still the case. For a data frame, it could be that he already does some pre-filtering for you. But sometimes you have multiple timestamps and it depends a bit on the way you want to see it. Some data, you can look at it in different ways. There's different case notions. And then maybe for one case notion, you need timestamp X, and for the other case notion, you need timestamp Y. So here you see roughly in the input data that I was using, I'm saying to this algorithm, use this as the case identifier, use this at the... But a good question, obviously you want it to be sorted on time if you do this. And then you would get, again, the same model. Then finally, to wrap up, if you want to do conformance checking, what you essentially need to do is you need to get your event data and you need to get a model. You can, of course, also use a model that you discover, whatever you want. And then you can compute what we call alignments. And alignments are these explanations that I explained earlier of trace event data in the context of a process model. And then you would get some output like this, where it says the create order was matched correctly onto the model, then an add item was correctly matched, then a submit order. This is essentially for routing purposes, so this says ignore me. And then send invoice was okay. Here you see that somehow the order goods activity has not been recorded in the data as it should. We also have some visualizations of these type of artifacts, but I didn't put it in the slides. So again, if you're interested in applying process mining and you want to use Python, then please consider using our open source process mining platform. And that was kind of what I wanted to share with you today.